So this brings us to the very fundamental law of nature. This is after conservation of energy. This is the second, probably on equal footing, most fundamental thing in nature. And I do mean that really even more so than Newton's 3 laws of motion. And at this point, you might go, wow, I thought Newton's law is probably, the starting point. But no, conservation of energy and conservation of momentum is. In fact, I'm going to use conservation of momentum to prove to you Newton's 3rd law. Now, you might remember I mentioned a law is something that does not have an explanation. But you remember I mentioned it doesn't have an explanation when it was discovered. So a law is something people observe, scientists do, they observe things and then they find out, hey, I think things seem to follow a pattern. Let me write that pattern down. And then you do experiments after experiments, tries to disprove it. But if you still cannot find a way to disprove it, it looks like it just happens forever, for a lot of scenarios at least. Then you can write down, hey, this looks like a general law. And do you know why it happens? Most of the times when people call it a law, at the moment of discovery, people don't know why it happens. However, this is the job of theoretical physicists and try to find out why things happen. And a lot of laws we are able to finally figure out from a more fundamental law. So if you have like 10 different laws of nature, it will be good if you can find one that you can start with that one or two and actually derive and find that, hey, the other ones are just variations of this one or this two, okay? And this is one of the case. So Newton's laws are actually all provable at least in the past 100 years. We figured out how that it is not a fundamental law, but the law of conservation of momentum is pretty fundamental. It has remained as the fundamental law for a long time. It's only the past around 70 years or so, 70, 60 years, we find out something even deeper than the law of conservation of momentum. But that's really cutting edge things. Well, 50 years time scale is cutting edge for theoretical physics development. But yeah, it's very modern way. But anyway, so now you will see why. So first, let me state the law, which is very simple. Actually, you can read it directly from the book. I'm not going to write it out. It's just the total momentum before and after has to be equal. The total momentum of the system remains constant. Okay, you can call it whatever you like, but I'll write it in equation form. So you sum all the momentum initially, it should equals to the sum of momentum in the final state. Okay, all right. So what does that mean? So let's see if I can have two things collide and analyze what are the forces on them, because we know how to relate momentum with force, right? Okay, so if object A and object B collide, right? So let's say they move together like this and they collide. The moment of collision, what do we know about the force? Well, they collide and probably they'll move apart first. Let's look at the kinematics first. They'll move apart. But why do they move apart? It's because at the moment of collision, B experiences a force on B by A, and A experiences a force, a normal force, if you will. I draw it round, but the point of contact, the force is normal to the point of contact. You can call it contact force in general, or a normal force in the sense that it is normal or perpendicular to the point of contact, the surface of contact, on A by B, right? But of course, let's say we don't know that force on A by B is the same as force on B by A. Okay, so how are we gonna use the law of conservation of momentum to figure it out? Well, let's first say, hey, this guy has a momentum PA initial, right? And this guy has a momentum of PB initial. Okay. Notice this is a vector. So if this is purely in one dimension, I can actually not write the vector sign and just write this is a positive value, this is a negative value, just but be careful. And over here, now it has PA final, because remember what is P, what momentum, right? It's MV. So the velocity has changed. So I should have a different label. If you don't like to write I and F, you can put a prime on it. Sometimes I'll do that, but here I'll stick with this. I started already. Okay, so what's the total initial momentum? The total initial momentum is PA of the system. The system is A and B together. So of a closed system, that's important. A closed system. Okay, just like conservation of energy, if you lose energy, you can lose it to the environment. If it's out of your system, that will be an open system. Okay, so PA plus PB initial must equals to the sum of final, which is PA final plus PB final. Okay, all right. Now let's see what is the change in momentum for A. So if I move that on this side, you'll see it's PA final minus PA initial vectors. And on this side, it is PB initial minus PB final. Let me put a negative sign. So PB final minus PB initial. Okay. So this is basically the impulse on A, or the change in momentum of A, right? And this is the change in momentum of B, right? So I just rearranged this. And now you realize that because there's two ways, there's many ways you can go about this. You can just say, let me divide both sides by time. And because the change, this is basically the average force applied on the object. So this is the force on A because the change in momentum on A. And this is the force on B. And now you can add to the label because force must be on something by something. So you will ask the deeper question of why did the momentum change? Why did it change from this to this? Well, it's because of B, right? So this force must be by B, and this force must be by A. You see what we got here? So the force on A by B is negative of the force on B by A. So equal in magnitude if you take an absolute value, right? If you take the magnitude on both sides, equal, but the direction, one vector, or if you just remember from day one when we learn about what is the negative vector, if this is pointing this way, this negative of it is just the vector pointing in the other direction with the same length. Okay, so you see that Newton's third law is really just a consequence of this. So this is one way to go about it. The other way I was gonna say is you can remember just when you get to delta A is negative of delta B, that just means the impulse on A is negative of the impulse on B, but impulse, right, which is change in momentum is F dt or F delta t over a same amount of time. So you can write this as minus F of or on B, and the change in time. What is the change in time? The change in time from this to this. Okay, so the change in time for B and F on A, the change in time. So this is that's sort of a more rigorous way to go about it. Really is from here to here. I'm just saying hey, this is change in momentum, right? Change in momentum is impulse, and this is change in momentum. So we'll write it like this. Okay, and the amount of time that A went from this to this is the same amount of time that B went from this to this. And that's the reason you can cancel out this and get the same conclusion. So that's a slightly more rigorous or slightly more formal step. But yeah, as you can see, this is, we can show you this. Now, you might actually another way to look at this and say, I can actually prove the law of conservation of momentum from Newton's third law, because I can start from this because every step is reversible. You can say, hey, maybe I like that to be more fundamental and go up. That is completely fine as well. So which one is more fundamental? Which one is a derived law? Which one is a fundamental law? That depends on which one can explain more things. Okay, and turns out counterintuitively, you might think it would be Newton's third law that is more important and it can explain more phenomena. But turns out no. When we went into quantum physics, when we find as theoretical physicists, when we study how the microscopic atoms work and then go out to the universe and look at cosmology and relativity, special relativity, general relativity, the idea of momentum remains, and it's very useful. Turns out the idea of force becomes outdated and obsolete in there. So for most theoretical physicists, in most of our work, we rarely talk about force. For engineers, it's useful, but for an astrophysicist, it's not that useful. The idea of energy and momentum is actually much more useful in a fundamental and deeper sense. All right, but nevertheless, as a beginner physicist, force is very visual. It's easier, like I said, there's pros and cons of everything. Force is very visual. It's a push and pull. It has direction. It's easy to visualize. But momentum and energy could be more abstract, right? Okay, so now we already see some examples of how this is relevant to collision. So let me pose a question, and we'll see how to analyze this in the next video. Okay, so here's a few questions. If I dropped an object with the mass right down here, and it bounces back to the same height, and this, so just drop a ball, whatever, it bounces here. Imagine there's no heat loss, right? There's pure conservation of energy. What is the velocity here? So let's say u is some speed minus 5 meters per second. Okay, like this. Assuming no friction, nothing, no heat loss, no sound loss. Technically, if you bounce something, there will be the flow will warm up a little bit. You will lose some energy to it, and there might be a sound, so you lose some sound energy. But assuming you don't, right? So assuming everything is conserved, what is the velocity over here? Another question is, if I send a mass with some velocity, let's say, again, our favorite number, 5 meters per second, hitting an object at rest, okay, so UA, UB, same mass, okay, and so they collide, what happens? What happens to VA? What happens to VB? Okay, so this is staying here, staying still, minding its own business until some guy come and hit them in the back, just like everything in life. And what will happen? So something here and some might collide like this. You might think, when do I care about this? Well, if you play pool, if you play billiard balls or play pool, right, or snooker, right, then you will have a snooker ball or a billiard ball hit one another. This is exactly the scenario. And if you have played that before, you'll know how this situation works. One more question is, what do you think this will happen? If I have a train car, same mass, similar situation, but I modify a little bit, okay? So this guy is at rest. Okay. This guy is moving 5 meters per second again, let's say, crashing into it. But this time, as soon as they crash into it, the two cars couple up, okay? So they're now tied together as one big mass. They're not gonna separate. And what will happen? Will the whole thing couple and stop? Will the whole thing couple and move? If they do move, so what is the combined velocity when after they have coupled together and combined, so they're not moving? What will happen? Okay, so give that a think. Without momentum, you will not be able to explain that yet. Well, that may be with some of your intuition. You will not be able to explain that yet. We'll show you how to calculate this. But with just conservation of energy, you should be able to answer this. So give that a try. Give that just, let's say, 2 minutes. See if you can figure out with just what you've learned. And we'll see if you get that right. And can you justify what will that answer